not be able to cover everything I had in mind, but that's okay. So I will summarize now what we have said so far about non-state space methods. That non-state space methods are easy to use and have relatively fast algorithms for system reliability, system availability, system mean time to failure, and to find bottlenecks. But the key assumption necessary for doing that is stochastic independence between system components. And the algorithms available are series parallel composition algorithms, factoring or conditioning algorithms, all min paths followed by sum of disjoint products algorithm, binary decision diagram based algorithms, and bounding algorithms for RL graphs. And all of the above are implemented in Sharp. But what we find in practice is that dependence is real. The failure and repair dependencies are often present in real life systems. And these methods we have developed so far, RBDs, REL graphs, F-trees, cannot easily handle these dependencies. There are maybe kludges, but at the bottom, they are really not pure RBDs, REL graphs, or fault trees. And there are many examples of dependencies: shared, repair, warm or cold spares, imperfect coverage, non-zero switching time, travel time for repair person, reliability with repair. There are many examples, and some of which I will provide to you, where dependence is there. And therefore, we are no longer able to use the methods we have discussed so far. So we need something more. And that something more is state space methods. And the most important example of state space method is a Markov chain. Now, so to model complex interaction between components, we need to use paradigms like Markov chains, or more generally state space models. And many examples of dependencies among system components have been observed in practice and captured by so-called homogeneous continuous time Markov chains. And extensions to Markov chains called Markov reward models makes computation of measures of interest relatively easy. And there are 3 of my books that develop Markov chains in great detail, the different types of details. You can choose any one of them and go to the others if you like later. The blue book, the first one I had published, a white book, the second or third one I had published, and green book. So all these books give you a lot of details about Markov chains and Markov reward models. By the way, my co-authors on the green book is right here, Andrea Bobbio. One of the co-authors on the white book I see also present here, Herman Demir. So I'm very happy to welcome my co-authors here. Okay, the other co-author, Gunther Boelsch, is no longer with us, so he couldn't be here, I'm sorry. And Stefan Greiner is not here either, I suppose. So we are now going from non-state space methods to state space methods, and in particular, homogeneous continuous time Markov chains, or CTMC. And my approach is going to be via examples. So I'm now going to show you the availability model of the cooling subsystem of IBM Blade Center, real life system that I developed jointly with IBM engineers. And what I want to show you here is cooling subsystem has 2 fans. So system is up and running with 2 fans, and each fan has a failure rate lambda c. So overall failure rate is 2 lambda c. 1 fan fails. At this time, you call for the repair person. So there is a travel time of the repair person. Repair person is on site, repairs the fan and puts it back up. In the meantime, before the repair is completed, the second fan may fail, or from this state itself, second fan may fail, etc. So I discuss with the engineer how does the system behave and reflect it by a state diagram and then eventually by rates making a Markov chain. And in this particular case, we have something called online repair. So repair is carried out and system is not brought down to finish the repair and installing the repaired fan. Travel time of repair person is separated from actual repair time, etc. So these kinds of things could not be accommodated in the reliability block diagram. Similarly, another example is the power domain subsystem model of IBM Blade Center, in which, again, two power supplies are up and running, and one of the two power supply fails at the rate 2 times lambda PS. But I asked them, is it possible that one power supply failing can bring the system down? And after some discussion, they said yes. So that is called an imperfect coverage. So it is possible that the first power supply failing will bring the system down with some probability, 1 minus CPS. And with some probability, first power supply failing, system doesn't fail. So these kinds of stuff, these kinds of notions of imperfect coverage or so-called common mode failure cannot be easily accommodated in the fault tree or reliability graph or reliability block diagram. You need a Markov chain for this. I developed Linux operating system availability model while working on IBM Blade Center. And Linux system is up and running. After some time it fails. There is some detection delay before the fact that the system has failed is discovered. After that, the natural thing to do is reboot the system. So, but the reboot may be successful with some probability and not successful with some probability. If reboot is not successful, then somebody has to be called and system has to be patched. So this is, there is detection delay here, imperfect coverage here, and 2 levels of recovery. Again, these kinds of things would not be easy to do in a fault tree or reliability block diagram. And I'll skip this slide. And things can get much more interesting. This is the model we developed of so-called replication domain of 2 app servers in IBM WebSphere. And 2 app servers are up and running here. One of the app server fails. After that, there are 3 different detection mechanisms. And detection mechanism, each detection mechanism may fail to work or not fail to work. And depending on the detection mechanism, the recovery type is different. And so these are great details of the system behavior reflected in the model. And this would be impossible to do with fault tree or a block diagram. You need Markov chains, no question, you need Markov chains. But what is also very interesting for those who want to know, in practice, the engineers are not aware of all the details of these kinds of modeling, or even in this particular case, even this recovery sequence, the sequence of recovery actions is not known to one individual, and it's not known in a manual. So I had to ask loaded questions. When the failure occurs of an app server, is there a detection? So my interface engineer will ask the question to many other engineers, and after some time they'll come back and say, yes, the detection may occur by a workload manager or a node agent. Then my question, is it possible that the workload manager is not able to detect? And again, 1 week later, the answer comes back, it is possible, and so on. And then what? Then there is manual detection. Then I ask, okay, now WLM is detected that the failure has occurred. Then what? What kind of recovery? They will say, if WLM is detected, then you fail over to the other app server in the other node. What if the node agent detects? Well, there is automated process restart and so on. So these questions, my loaded questions, were responsible for discovering the recovery behavior of the system after a failure. Interestingly, it was not known, it is not documented anywhere, and this is probably still true. And so experienced modeler is necessary in order to actually develop such models, because even the information about the details of system structure are not available. So this is a real life system model of WebSphere application server.
Kishore, there is a question in the chat. So one student is asking if there are some way to validate these diagrams that actually, as you said, needs to be done by an experienced reliability engineer, right?
Validation is a very interesting question. So in this particular case, so when after I develop the model, I go back to the engineers and explain. So first of all, these engineers have never heard of Markov chains or anything like that, but they do know state diagrams, right? Or state graphs or whatever, state charts. So I go through in detail. Is this what happens? Is that what happens? Is that what happens? And many times they will say, no, you misunderstood what I had in mind. This is not what happens. So I change the diagram. So we keep doing that, iterate between the engineers who know the system well and the modeler. And after some time, everybody agrees. And this particular method of validation is called face validation. Everybody's face lights up, their smile. That is face validation. There are other methods of validation that if we have time, unfortunately, I don't think we'll have time to discuss everything like that, but validation is a very, very important topic, and it is much harder in the context of reliability and availability than in the context of performance, because the time scales are very different and so on. But it's a very important topic that not more work is necessary. All right?
Okay, thank you.
So now I want to very quickly go through another example of reliability now. So far, examples of Markov models that I've given you were availability examples. Now I will give you reliability example. And again, this is a very simple example, but illustrates some very important points. So suppose that you have a single component, like a disk or whatever, and suppose that time to failure distribution is exponential. We have taken a very simple case. It can be developed with anything else. So the reliability function is e to the power minus lambda t. Lambda is the failure rate, and the mean time to failure is 1 over lambda in this case. And the corresponding reliability model can be shown to be very simple like this, that initially system is in up state 1, and after at rate lambda it fails and goes to state 0. This is a reliability model. Reliability model will have always one or more absorbing states like this. This is an absorbing state. And availability model will have no absorbing states that we have seen all along so far. Now suppose that you use redundancy. You use 2 disks instead of 1 disk, for example. They are called mirrored disks. Then the corresponding model will become, initially you are in state 2. At the rate lambda, each disk fails. So overall rate of lambda is 2 lambda, overall failure rate is 2 lambda. Then you enter state 1. One disk is up and running. The other disk has failed. And at the rate lambda, the second disk may fail, and system as a whole fails. Now, it is not very difficult to find the reliability expression for this particular situation. And it is given by 2 e to the power minus lambda t minus e to the power minus 2 lambda t. And the mean time to failure, system failure in this case, is 1.5 over lambda. So the mean time to failure increases from 1 over lambda for this system without redundancy to 1.5 over lambda with system with 1 redundant component. So redundancy improves reliability and mean time to failure. But now suppose that I also do repair. So after the failure of first disk, I consider the repair of the first disk, but it is possible occasionally that the second disk fails before the first disk repair completes. Notice, however, that more than likely this will succeed over that, because the rate of repair is much, much larger than the rate of failure. So more than likely you will be cycling in this particular loop. So this is redundancy and repair combined together. And we are hoping that this will make us fail very rarely. And this can be analyzed, and these are details given here. And I can find the expression for reliability of the system where both repair and redundancy are done. And this is the mean time to failure expression for the system with reliability and repair. Notice that the first part is 1.5 over lambda, which is the effect of redundancy alone. The second part is the added effect of repair with redundancy. Notice that mu may be of the order of 1 in few hours or something like that, or few whereas lambda may be 1 in 10,000 or 1 in 100,000 hours or something like that. So this is square of lambda. So there's a huge gain by having redundancy together with repair. So this can be documented in several different ways. This is the reliability of the three cases. This is reliability without redundancy. This is reliability with redundancy. Reliability with redundancy. Why did the pointer go away? Okay. Reliability with redundancy, but no repair. And this is reliability with redundancy and repair. It's way out there. Alternatively, this can be seen. There was a practical example in one paper somewhere long time ago. It was observed that the mean time to failure of a single disk is 6 years. So redundancy alone with one hot spare will yield one MTTF of 9 years, 1.5 over lambda, remember? Mean disk repair time was observed to be 5 hours, and redundancy with repair then yield an MTTF of, according to the expression earlier, 31,000 some years. But then somebody collected the data and estimated from the data only 1,300 years. So instead of going from 9 years to 31,000 some years, only got 1,300 years. So this needs to be explained. That paper never explained. So what do we do? Okay, so this is the picture now, that first disk failure may be recovered from, and the second disk continues to function, but occasionally first disk failure itself will bring the system down with some probability. So this is the imperfect coverage. When I throw this in and rederive the reliability and mean time to failure, I get a different expression. And now I can explain what happened in that particular data. So if I have the coverage probability very high, 0.9978, it brings down the mean time to failure to 1,300 years. So what I'm trying to say is that real life data can be validated against models if you like, if your models are powerful enough. Many people in practice don't know the notion of imperfect coverage and details. They can be reflected with Markov chains, unfortunately, and they use useless models, and their models cannot be validated then. Okay, so what is happening down below when I do a continuous time Markov chain? Well, efficient and scalable algorithms are known and are implemented in software packages like Sharp, SPNP, and many others. And the steady state behavior amounts to taking the matrix of the Markov chain, so-called infinitesimal generator matrix, and solving the linear system of equations pi q equal to 0. Except q may not be 4 by 4 or 3 by 3 or something like that, but million by million or 10 million by 10 million. And transient behavior amounts to solving the differential equation d pi by dt equals pi t q, once again with q being a million by million. And cumulative transient behavior amounts to solving the another differential equation. And derivatives of the probabilities with respect to parameters, so-called parametric sensitivity functions, can also be computed, and efficient algorithms are known for all this. They have been implemented in the tools. So now whenever somebody shows a homogeneous continuous time Markov chain, somebody from the audience will say, hey, wait a minute, you have used the assumption of exponential distributions everywhere. And I said, yes, but it is possible to relax these assumptions by using semi-Markov process, Markov regenerative process, non-homogeneous Markov chains, or phase type expansions. And these methods are detailed very well in our green book. So algorithms exist for solving, developing and solving such models. Only problem is oftentimes people don't have the data to drive such models. The methods are not lacking, it is the data that is lacking, in my mind. So don't let somebody tell you, because you're in exponential assumptions, your models are not useful. We can extend, we can capture non-exponential distributions very easily. So the question now is that, have we found the final answer, namely continuous time Markov chains. Well, yes, they can model all kinds of fault tolerance behaviors, all kinds of recovery and repair behavior. They can model all kinds of dependencies. They can model contention for resources, concurrency, performance, etc. They can be generalized to Markov reward models to model degradable systems. They can relax the exponential assumption to lead to SMP, MRGP, NHCTMC, etc. So have we found the panacea? Have we found the final answer? Well, and in a sense, yes, the performance, availability, performability, survivability, resilience, all this modeling is possible. And we have demonstrated that, and many others have demonstrated that using real system examples. Only problem, and the key problem is that the number of states that you will need to capture any real life scenario will be so large as to be impossible to handle, So rest of the discussion is on how to deal with large state space, whether it is for reliability and availability, or for performability, or survivability, or performance, or resilience. Dealing with large state space or security, dealing with large state space is the key problem of any such models. So Markov models, modeling interdependence among components, simple model types such as reliability block diagrams, fault trees, etc., do not suffice, and we need to use Markov and other state space model types. But state space explosion is the key problem to deal with. So how do we deal with state space explosion? Well, there are two broad categories of methods that I have been talking about. One is what we call largeness tolerance. So what we'll do is we'll provide a high-level formalism to the user of such tools and such models. And this formalism will be succinct and will be able to, you will be able to express the model in this higher level formalism, even for a very large system. And it is the tool that will develop the underlying Markov chain or state space, if you like. And this state space will be automatically generated, stored, and solved. And there are a number of different formalisms, high-level formalisms. And the one that we have worked with is based on stochastic Petri nets. But there are many other formalisms that have arisen that allow you to express the problem at a very high level. And the tool will transform the high-level formalism into the underlying state space of a Markov model or what have you. And let me illustrate this. And this method I call largeness tolerance, because large model is actually generated, stored, and solved. Therefore, we are tolerating largeness. We are not avoiding largeness. And let me illustrate this through a simple example that we helped do at IBM. So IBM, this is IBM Research Cloud, which was around 2011 or so. I think IBM approached me to help them develop actually performance and availability and performability model of this research cloud. I'm only showing you the availability model here. Performance model and the optimization model is all documented in papers. Want to know? I'm only giving you the availability model here. And so the key idea that I liked in my development of the models, and that's why I got excited, is that IBM had this idea that they will divide the physical machines or servers into 3 pools to reduce the power usage. Because I've been told now that the data centers, the major cost of running the data center is the power, not the acquisition cost of hardware or software or any other, but only power. So to reduce the power usage, they propose that the machines can be divided into 3 pools: a pool of hot machines, a pool of warm machines, and a pool of cold machines. The idea is that hot machine will have high power usage, and it's a high performance. Very quickly, you can schedule the virtual machines and give them to the users but the power usage is high. By contrast, a cold pool machine, power usage will be very low, but the performance will be low because it will take a while before a virtual machine in the cold pool can be allocated to user, and warm pool is in between. So, and this idea, a similar grouping of physical machines is also recommended by Intel now. So what we're talking about is relevant to more than one system. So for availability model, we observe that the physical machines can fail and can get repaired. And a minimum number of operational hot physical machines are required for system to be functioning properly. So if the number of machines in the hot pool goes below the threshold, then physical machines in the warm or a cold pool can migrate upwards to the hot pool. And similarly, upon repair, physical machines can migrate back to the original pool, that is cold or warm pool. And so this introduces an interesting dependence that would not have been there otherwise. And so originally we developed the model first. And we wanted to develop a Markov model for it, but Markov model will be too large to construct by hand. And therefore, we said that we will use a high-level formalism, and our formalism is called Stochastic Reward Net, which is a development over Stochastic Petri net. And such SRN or Stochastic Reward Net models can be automatically converted into underlying Markov reward model and solved for the measures of interest such as downtime in minutes per year, steady state or instantaneous interval availability, reliability, derivatives of these measures of interest, all numerically by forming and solving the underlying equations. So this is a analytic numeric solution as opposed to discrete event simulation. And the key, there are several key papers on SRN, but this particular chapter in a book, Linear Algebra, Markov Chains and Queuing Models, is probably as good as any, giving all the details of our tool called SPNP. So Stochastic Reward Net model for that particular IBM Research Cloud is shown here. And I don't mean to go through details of it. It will take another hour to explain stochastic Petri nets and stochastic reward nets. But what is shown here is in this place, I put in the number of tokens equal to the number of machines in the hot pool. Similarly, number of tokens here is number of machines in the warm pool, number of machines in the cold pool. The machines can fail and get repaired, and machines can migrate from warm pool to the hot pool, or from cold pool to the hot pool, and so on, and migrate back to the original pool after repair and so on. And there is a lot of additional stuff here. The guard functions are given here too. But in any case, depending on the number of NH, NW, and NC, the underlying Markov chain will be larger or smaller, but the user doesn't care. It is the tool that takes care of generating the Markov chain and storing and solving the Markov chain. So, and many other high-level formalisms exist like SRN, and can generate and store and solve moderate size Markov models, maybe 10 million states or something like that, and have been extended to non-Markov and fluid models. Two of our formalisms, MRSP and Markov regenerative stochastic Petri nets and fluid stochastic Petri nets, are very interesting formalisms in themselves. And for MRSPN, the key paper is in Performance Evaluation 1994. And for FSPN, key paper is in European Journal of Operations Research in 1998. So this SRN model, automatically converted into CTMC, gives rise to the following. So I've shown here the cases that we could solve. So when I say 3 here, it means 3 machines in the hot pool, 3 machines in the warm pool, 3 machines in the cold pool. So overall 9 physical machines. The underlying states, number of states is 10,272, and the number of non-zero entries in the Q matrix is 59,000 something. When we went to 777, so 21 total machines, we had 4.8 million states in the Markov chain and almost 42 million non-zero entries in the matrix. And when we went to 888 in that particular workstation, the memory overflow occurred. So the point is that scalability of this method, which we call largeness tolerance, is limited. And so problems with state space explosion is still open. And so the next method is what we call largeness avoidance. So we develop a multi-level models and compose the solutions from one model into another. And typically, our models will tend to be at the top level fault tree or reliability block diagram, at the lower level Markov chains. And many practical examples of use of these hierarchical models that we have developed, and can also use state truncation. Again, we have developed that. But this method is called largeness avoidance. A large model, overall large model, single monolithic model is never developed, never stored, never solved. We solve submodels and compose submodel solutions together into the overall model solution. So let me show you several examples of this, but the green book contains a huge amount of material on this topic. So what we have now moved from, originally we started at the non-state space methods, which are very efficient and very simple to use, to state space methods, particularly Markov chains, which allow you to capture dependency. But now we go to hierarchical model composition to avoid largeness, which is a key problem with the state space methods. And there are two principal books where you find a lot of information about hierarchical composition. This is the red book that we developed around 1997. This is primarily talking about Sharp and the methods implemented in Sharp. And the green book has a huge amount of material now on this hierarchical composition. So state space explosion problem is that the number of components in systems can be hundreds, maybe thousands. And the number of states in a Markov model will be a gazillion, as my grandson will say, whatever gazillion means. So we need to be able to control the state space explosion. And this we do by means of the largeness avoidance methods, multi-level modeling or hierarchical composition. And H in the Sharp acronym stands for hierarchy. So use of state space methods for those subsystems that require them because dependency is heavy, and use simple non-state space methods such as RBD and fault tree for the more well-behaved part of the system where either dependence doesn't exist or it is very weak. So let me illustrate these ideas by simple examples. So let me go back to the Sun Microsystem example that we had earlier seen. It's a carrier grade high availability software platform and model taking into account hardware component failures, software component failures, and various types of recovery. And hierarchical model composition will use Markov chains at the lower level and reliability block diagram at the top level. And the reference is a paper in PRDC Pacific Rim Dependability Conference 2006, published with myself, one of the graduate students, and several people from Sun Microsystems. And of course, this problem is also documented in the Green Book. So overall model, top level model was a reliability block diagram that we saw earlier. And each of the submodels that are in red, each of the top level block that is in red was developed as a Markov chain down below. And again, with a lot of discussions with the engineers who know the system well. And I'm not showing you all of the models, submodels, but and so the idea is that Each of these submodel is solved separately and answer is supplied up the chain. And so this is a two-level hierarchy. And this hierarchy can be represented by what we call import graph. So top level block, model is a block diagram, RBD, and a bottom level power supply subsystem Markov model, fan subsystem Markov model, etc. And each of these submodel, the solution of the availability of that submodel is supplied as input to the top level model. So this is the import graph of a hierarchical model. And this is what we typically do. Single monolithic model is never generated. Now let me illustrate this same idea with another example, real life example. And this was with IBM. So IBM had developed this particular system, real problem from IBM, and they had implemented the session initiation protocol on hardware platform called IBM Blade Center, and the software platform was IBM WebSphere. And they wanted to sell this system to a telco giant, telco customer. And they showed the architecture to the telco customer. But telco customer said that they need some quantification. The architecture sounds good, but they need some real numbers to be able to decide whether they will buy the system. So they asked for two models from IBM, an availability model and what they call reliability model. Now it turns out IBM is a very large company. So the particular set of engineers that were dealing with this system, they had no idea what that meant. And somebody happened to mention to them that there is this fellow Trivedi who can probably help you with this. So they approached me and asked them to develop the models that the telco customer needed. And as an outsider, I was in charge of the modeling project. And we developed two models, one availability model and one actually turns out to be DPM model. And both were eventually published. But because of these two models, we are told that the telco customer bought the system. Now, there's a lot of story behind this particular real life problem. And I'm only going to tell you about the availability part. I'm not going to tell you about the second part, which is also very, very interesting. And some other time, maybe if I do this summer course, 2-week course, maybe I'll get a chance to tell you about that part. But in any case, let me start with the architecture of the system that was provided to me when I started that project. And so this is the picture they gave me. And in the picture, what we find is that there are two blade center chassis, blade center chassis 1 and chassis 2. And each blade center had 4 blades or 4 nodes, blade 1, blade 2, blade 3, blade 4. And each blade node had Linux operating system on it. Apart from the operating system software, it had also 2 application softwares. One was called SIP proxy, and the other is called application server or WebSphere application server. So application server will be denoted either as AS or WAS, standing for WebSphere application server. Furthermore, there were 2 SIP proxies, 1 in each box, and there were 12 copies of the app server, 6 in each box. And 2 app servers shared one blade server node. And app server 1 labeled 1 in chassis 1 is connected with app server labeled 1 in chassis 2, and this is called a replication domain. So this information that I gave you is condensed in the next chart here. It's hardware configuration wise, they employ 2 blade center chassis, 4 blades each. Now they also told me, maybe after I asked them, that 1 chassis would have been enough from the perspective of performance, that is throughput requirement. But they use 2 chassis for redundancy. for availability, high availability. Software configuration wise, what we saw is that 2 SIP proxies are used, and they told me that one would have been enough from the performance or throughput perspective. So they are using redundancy there too. 12 copies of app servers are used, although 6 would have been enough from the perspective of performance. So once again, there is redundancy. And furthermore, each VAS instance forms a redundancy pair or replication domain with VAS installed in another node on a different chassis. So the system has both hardware redundancy and software redundancy. But the software redundancy is very different from what is found in the literature, in the academic literature, in the books. Identical copies of SIP proxy, identical with the same bugs, if you will, is used to back each other up. Identical copies of the FCR application server used to back each other up. And so type of redundancy used for software is not design diversity, which is what the entire literature on software tells you, but replication of identical copies, much like we do in hardware. So software is beginning to look more and more like hardware. Then I asked them, when a software failure occurs, if proxy fails or app server fails, what is the action? Normal recovery after software failure is using time redundancy. What is time redundancy? Restart the app server. If that doesn't work, reboot the node on which the app server is located, or fail over to its replica in the replication domain in the other box. Only when all else fails, a software repair is invoked. So this is very different from what the literature tells you. Time redundancy and identical copies, replication of identical copies is used for redundancy for software failures also. So the classical techniques that we learned briefly earlier were based on design diversity. Diverse copies of software are produced to the same specifications, and then recovery block or inversion programming are used. What we find is this design diversity is too expensive because producing one version is costly enough. Now you are asking me to produce multiple versions. So it's a very expensive solution, which is then relegated to safety critical or life critical applications. It doesn't get used very much in the enterprise systems, yet stringent requirements of failure-free operation exist even in those systems. So what we then need is affordable software fault tolerance as opposed to the expensive software fault tolerance that is provided by the classical techniques which you find in the textbooks. And the affordable software fault tolerance, we call it environmental diversity. And there's a brief foray into this, which will be explored in greater detail next week in my Tuesday's webinar by IEEE Reliability Society. So retry, restart, and reboot have been known to help with in dealing with hardware transient faults. But now they are being advocated in dealing with soft failures caused by software bugs without fixing the bugs. So if this should help, why should it help? Similarly, failure to an identical software replica that is not a diverse version and therefore has the same bugs as the original software that failed. Why should it help? And if I proposed something like this 35 years ago, I would be put in a lunatic asylum. I would be considered crazy. But today, we just saw in a real system this being used, advocated and being used. And then subsequently, I found in many other systems that this kind of idea is being used. So the new thinking in software fault tolerance is environmental diversity as opposed to design diversity, or in addition to design diversity. So what is environmental diversity? Well, our claim is that retry, restart, reboot, and failover to identical software copy may well work since failures due to Mendel, what we call Mendel bugs, are not negligible, and we thus have an affordable software fault tolerance technique that we call environmental diversity. And quick references on these topics are given here. One in IEEE Transaction on Reliability 2020, another is IEEE Transaction on Reliability 2016. So in order to proceed further, very briefly, I will introduce the notion of these different types of bugs. And so we talk about something called Bohr bug, a bug that is easily isolated and that manifests consistently under a well-defined set of conditions because its activation and error propagation lack complexity. And this is, I submit, is the only mental model of bug that we have been carrying all along. By contrast, there are now bugs which may be called Mendel bugs, a bug whose activation depends on the environment besides the workload. So it is not just the inputs that you supply, explicit inputs that you supply to the program, but also the environment in which the program is executing that determines whether or not the bug will manifest itself as a failure. And by environment, we mean the other applications concurrently running in the system, as well as the interactions between your software and the operating system resources, as well as hardware. And one other type of bug that we have discovered that is relevant is what we call aging-related bug, a bug that leads to an accumulation of errors either inside the running application or in its system context environment, resulting in an increased failure rate or degraded performance. That is, software appears to age just like hardware, and therefore the preventive maintenance, which we call software rejuvenation, is possible to help improve system availability and system reliability against software bugs. And if you want to know more about the classification, the first paper to read is this IEEE Computer Magazine paper in 2007, which we call Fighting Bugs, Remove, Retry, Replicate, and Rejuvenate. And this is perhaps the only paper I have written in which there are no equations whatsoever. This is only text and some pictures. There is also the handbook of software aging and rejuvenation that details at least this particular phenomena, aging-related bug and software aging. So dealing with Mendel bugs, failures due to Mendel bugs can be tolerated by retrying failed operation, restarting a process, or rebooting the virtual machine, or failover to an identical replica, because the environment has changed enough so that the same bug may not be excited by the same workload. And failures due to aging-related bugs can be prevented or postponed by software rejuvenation, which is a preventive maintenance technique, which is detailed in the handbook on software aging and rejuvenation. So what is environmental diversity? Just to very quickly capture that idea. Underlying idea is that we start an application without fixing the bug, and it most likely works. Why? Because the environment where the application is executing has changed enough to avoid fault activation or reactivation. Our environment is understood as the OS resources, other applications running concurrently and sharing the same resources, interleaving of operations within your application, concurrency or synchronization. This is fault tolerance, since we do not necessarily fix the fault caused a failure, but this failure is dealt with by using time redundancy. Hence, the user may not experience the failure again on retry. And as I said, if you want to know more about this, there is this webinar next week, Rethinking Software Fault Tolerance, on Tuesday, November 16th at 11 a.m. Eastern time, or 8 a.m. Pacific time, and the link is given here, but you can also find that link on my ResearchGate page or on my LinkedIn page and so on. So now coming back to the original problem of SIP availability model, we go back and look at, I'm sorry, I have one more slide on study of bug types in real life systems. And I'm not going to go through details again. Next week, you can see this. But we have actually analyzed the real life bug reports and discovered that reasonable percentage, large percentage of bugs in real life systems are Mendel bugs or aging related bugs. And therefore, this environmental diversity technique can help. Now, going back to the original model of SIP on IBM WebSphere, we counted the number of components, both hardware and software, that can fail were 112. And so the monolithic Markov model will have at least 2 to the power 112 states. So we are not going to do that. But first we divide the failures, potential component failures, into the hardware and software. So on the one side, we have physical or hardware failures. Power subsystem may have faults, cooling subsystem may have fault, each blade may have faults, wind plane may have faults, network that is connecting may have faults, and blade has many subsystems. On the software side, we have operating system, we have applications wise, we have WebSphere application server and the proxy. So each of these components may fail and has a recovery sequence. And so we want to capture all that. So at the top level, we decide, so single monolithic Markov model will have extraordinarily large number of states. So we use a multi-level approach. Subsystems are modeled using Markov chains to capture dependence within subsystems. And fault tree is used at the higher level, as independence across subsystems can be reasonably assumed. And so this is an example of hierarchical composition. A single monolithic model is not constructed, stored, or solved. Each submodel is built and solved separately, and results are propagated up to the higher level model. And our software package SHARP facilitates such hierarchical model composition. So very quickly, at the top level, I've developed the fault tree, and it's not too difficult to understand. Basically, from the user perspective, app server and proxy server should be accessible for the system to be up. So since there are 2 proxy servers, both proxy servers have to fail for system to fail. That's why there's an OR gate here and AND gate here. Now, what does it mean for a proxy server to fail? Proxy software may fail, or the blade server hardware on which this proxy is located may fail, or the chassis common on which this blade server is located may fail. So any one of these 3 failing, that proxy will not be accessible. And if both proxies are not accessible, system fails. Similarly for the app server. Notice, however, that the chassis common is common between many different subnodes here, and therefore there's a repeated event. So repeated events is very common here, and that's why we chose a fault tree rather than a block diagram. And then we developed at the lower level, there are some submodels which are fault trees, and at the bottommost level, there are Markov chains. And so in between fault trees and in between the lower level Markov chains, I've shown you some Markov chains earlier. And so the overall model can be seen as a cartoon like this, that Markov submodels solved and feeding answers into upper level, middle level fault trees, and finally propagating all the way through to system level answer, system availability or reliability. And this is model composition. Individual submodels are solved and their solutions are propagated up the chain. This is not model decomposition. This is model composition. And you can see the overall structure of the models connecting with each other through, again, this very simple import graph in which the submodels are solved and answers are supplied to the upper level models and so on. And then in order to solve the model, finally, we need to supply input parameters. So I divided the input parameters for such a model into 4 groups: hardware component failure rates of individual hardware components, software component failure rates. We have 3 software components, remember, in this particular case. And then after failure, there's detection delay, restart delay, reboot delay, repair delay. And furthermore, each of these phases may have the imperfect coverages. That is, detection may fail to work with some probability, restart may fail to do its task with some probability, etc. So these imperfect coverages, these 4 groups of parameters. And these parameter values can be in general obtained from field data for hardware component failure rates and testing for some of these some of these rates like detection rates and restart and so on. And sometimes we don't have any information, then agreed assumptions on some parameter values. And for those parameter values where we don't have a answer, then we do uncertainty in those parameter values by means of sensitivity analysis, that parameter with respect to that parameter. And so this is the list of parameters that we used. Now, these are not the actual values. Actual values are confidential, but the list of input parameter values. So I think there are 67 input parameters, if I'm not mistaken. And after that, you can find the answers and argue. And the answers can be, so this system downtime is decomposed into overall system downtime, decomposed into operating system contribution, hardware contribution, proxy server contribution, app server contribution, and the overall downtime and so on. So, so contributions in this particular exercise that we made is we developed a very comprehensive availability model with details of hardware and software failures, hardware and software failure detection delays, software failover delay, escalated levels of recovery, including automated and manual restart, reboot, repair, imperfect coverage, and these details with which we had developed the models itself impressed the customer, IBM's customer, that that led them to actually accept the system. And model parameters were collected from experiments, some obtained from tables, few of them assumed, and detailed sensitivity analysis to find bottlenecks and give feedback to the designers. And we also developed, which I'm not telling you about, new method for calculating the number of calls dropped due to a failure. And we were told explicitly that these 2 models were responsible for the sale of the system by IBM to the telco customer. And all the details of this are provided in the Green Book. So let's return to this hierarchical composition that we have been talking about both in the Sun microsystem example and in the IBM SIP example. Many more examples of such models can be found in the Green Book. And this is in the context of availability models, reliability models, performance models, performability models, survivability models. You find examples of all this in the Green Book. And what we can also theorize that a main reason for hierarchical or multi-level models is to avoid generating or solving large monolithic models. And so that is why you get tractability or scalability with this idea. And in short, we can mix and match different paradigms to arbitrary levels of hierarchy. And we can choose the right paradigm for each subsystem, whatever that means, in particular, depending on the type of information available, type of system that is being discussed, and so on. And I will note that some tools or approaches use hierarchy merely for specification. And a monolithic model is constructed by the tool, in which case hierarchy is not very useful. What we are advocating is hierarchy not just for specification, but also for solution. Hence, we are calling it hierarchical composition. And hierarchy does not always mean an approximation. Examples of this are given both in the Red Book as well as in the Green Book. And most practical problems I have solved have 2 or more levels, with the top level being a reliability block diagram or a fault tree, and Markov models at the lowest levels. Now, hierarchical composition requires a decomposition somewhere. The decomposition can be done at the matrix level, at the model level, or at the system level. Most often what I've seen in practice is the decomposition is done at the system level. Sometimes the decomposition is done at the model level. I will soon show you one. And I don't think it is very useful to do decomposition at the matrix level. There used to be a lot of effort along these lines, and there is a famous monograph by P.J. Kotua on matrix level decomposition. And my problem with this is that in practice, generating the matrix itself is an impossible task. So talking about decomposition at the matrix level is mostly theoretical. In practice, my problem is that matrix itself generation is impossible. So that is why I talk about either model level decomposition, that is at the Petri net level, for instance, or at system level decomposition. Now, we don't have a very good, or any for that matter, formalism to express such multi-level models. We need to develop a meta modeling language, and I have tried a little bit in my effort, but a lot more effort is necessary, and a lot more people need to agree with this idea of developing a model level formalism. One example of what I have shown you is what we have called import graph. So, and the other questions that need to be addressed is what kind of quantities can be passed between one submodel to another. And by doing this hierarchy, are we getting an exact answer or an approximate answer? It depends. And if approximate answer, can we bound or estimate the errors of approximation? There are some examples, some papers that deal with this, but a lot more work is necessary in dealing with this. But now the final question is the import graph once developed, is it acyclic or not acyclic? So far, we have seen two import graphs, one for the Sun microsystem problem and the IBM SIP problem. Both import graphs were acyclic. Now we will see an import graph that is not acyclic and will need something more called fixed point iteration. So we now advance from the hierarchical models to fixed point iteration. And we return to the IBM cloud example. And there is a chapter on fixed point iteration in the Green Book. So you will know a lot more about it in the green by that chapter. And so return to the IBM cloud example that we discussed earlier.
Sure.
Yes.
Maybe before you proceed, because I think the fixed point iteration is a separate topic. There are two questions in the chat. I mean, the first one is related also to what you mentioned on deriving the models and so on. So there is a question by Shahid that is asking if this question is back to the stochastic reward network. And but I think if we want to make general, this question is if we have, today we have some popular languages to describe the system. Like, I don't know, I'm familiar with the Tosca, which is a new standard in Europe to describe, for example, the cloud infrastructure in a way that you describe really the nodes, you describe the software, the dependencies of the software for the deployment actually. And the question is a way from these new descriptions to generate this stochastic reward network or any of these models that we are considering today?
Very good question. And there have been efforts, but I don't know whether there is a standardization of any kind right now. But there have been efforts to take UML, for example, and SysML to translate them into stochastic reward nets or other formalisms. There was an effort by Fumio Mashida at that time he was with NEC in Japan. Now he is with university in Japan. But he worked with me a little bit to take SysML and translate SysML models into stochastic reward nets and connect with SPMP. And there other efforts have been in a different direction. So special languages were developed. One example is with IBM, we helped develop something called SAVE, S-A-V-E, which was a language description of the system availability model, which will be taken in and then translated into these kinds of models. similarly, at Boeing, we developed an internal language for Boeing, and that's also well documented in papers. And that language is being used by Boeing today. It's a model description language. It's a special language developed for reliability and availability models for Boeing engineers, which will be taken in by the tool that we developed and will be translated into the input language for many different software packages, not just our own Sharp and SPNP. So there have been efforts, but I don't know whether there is a universally accepted method, but scattered methods are there, and I can supply more details of this if anybody is interested. There's a lot of work, but it needs to be consolidated and further developed so that we have direct access to all these capabilities from the system description languages like SysML and UML and so on. Okay,
thank you. That's the first one. The second one is related actually to the use of Bayesian networks. So, I mean, the student is Otto, is asking if Bayesian networks have been used for modeling reliability. And I mean, your general thought on this use of Bayesian networks for availability studies.
Yeah, so this is where I would pass on the question to Andrea. I've not personally worked on Bayesian networks, but Andrea Bobbio has worked, and it has been put in a little bit in our book, but not extensively, because I don't know that much about the topic. But Andrea, you want to take that question?
Yeah, is he still connected?
Yeah, we have worked on Bayesian network and mainly on the translation of fault tree to Bayesian networks, and then to show how Bayesian networks can provide much more quantities than fault trees, because you can do forward analysis like in fault tree, but also backward analysis that give you some sort of diagnostic profile for the system. And we have some papers on that are also included in the Green Book. So if you look at the Green Book in the fault tree chapter, the last part of the Green Book is related to the Bayesian network. So you can do to the look at the Green Book and look at the final part of the fault tree chapter.
By the way, now that we're talking about, and Andrea, I appreciate very much you being there and being able to answer the question. But I want to also emphasize that one of the things that I was very insistent with the publisher of the Green Book is that make it as cheap as possible. I would like it to be free, but publishers don't do that. But it is a lot cheaper than my other books, because that already always bugged me. Why are the books so very expensive? But anyway, so it is a relatively cheap book, I think. All right, is that all, Danilo?
Yeah.
Is there any other question?
These are the main question we received so far. So thank you, and maybe you can, if you want, you can proceed.
Okay,
thank you.
So I'm returning now to the cloud model, and here is what we had as a stochastic reward net as a monolithic model of the cloud, and we noticed that these are actually three submodels, and they are interacting at the stochastic reward net level. So the idea then would be, can we decompose this model into three submodels, which will be interacting with each other, of course. And so now I'm doing a model level decomposition, not a system level decomposition, but model level decomposition. But this is not matrix decomposition. And so what we ended up doing is that we constructed three submodels. One for the hot machines model, another is the warm machine model, and a third is a cold machine model. But these are not independent. They actually communicate with each other, and we have indicated that by additional places and additional transitions and some guard functions, and their intercommunication is now given by this import graph. So we have these three submodels in the import graph. Remember, I'm trying to do the meta modeling language, if you will, by this import graph. So I have three submodels, which are three sub Petri nets, see 3 SRNs, stochastic reward nets, hot submodel, warm submodel, cold submodel. And my design of the interaction is such that in order to run the hot submodel, I need some input parameters, and one of the input parameters comes as an output of solving the warm submodel, which is P sub W, whatever that means. I'm not going to go through details. Similarly, from the cold submodel, after running that, I need an answer called P sub C as an input for me to run the hot submodel, and so on. Now, what you notice is the import graph is cyclic. It is not an acyclic import graph. In other words, as it is, I cannot solve any submodel to start with. So I need to cut the graph somewhere. And so these kinds of problems can be cast as what is called a fixed point problem in scientific computing or numerical analysis. And basically, in order to deal with such problems, we have to answer many questions. So one question is, does a fixed point solution exist to such models? Now, it turns out that in 1996, we have written a paper way back, Varsha Menker and myself, in IEEE Transactional Software Engineering, that says in a very general setting, the answer to this question is yes, if those conditions that we set out in that paper are satisfied. The second question is that does this fixed point problem that we pose, does it have a unique solution? Now, this is a much harder problem, and in some cases, we are able to show that there is uniqueness, but a lot of work is necessary. And then the actual way of solving such problems turns out to be iterative. And so the question is, what is the rate of convergence of such iterative methods? And then what is the accuracy that you obtain by solving this problem this way rather than original monolithic model? And how scalable is this approach is? And so there are many questions, and I would like to see many more PhD theses devoted to this topic of fixed point iteration in reliability, availability, performance, performability, survivability, resilience modeling, security modeling. Coming back to our specific problem, remember that monolithic model could only solve 777 problem, but by interacting submodels, this fixed point iteration, we are able to solve 100 problems, so 300 machines fairly easily. And if you work harder, we could probably go to 1,000 too. So real life problems can be solved if you resort to such fixed point iteration and hierarchical solution methods. So in general, now returning in general, what have you been doing? Steps for solving system availability and reliability models. We have to list all possible component level failures. Many times, sometimes we unnecessarily approximate and not consider some components having failed. Maybe your model is as useless as your assumptions then. List all possible methods of detecting the failures of individual components and match with the failure types. List all possible recovery mechanisms and match with failure times. Now, my experience suggests that in practice, you need to ask very pointed questions to get answers to this. Otherwise, you may get very little information and your models may be useless because details of detection, recovery, etc. are not considered. We have not here worried about the allocation of software modules to hardware modules. We were told that SIP proxy is in this node and WebSphere application server is in this node, etc. We could also change that and make it a decision problem and optimize that configuration and get optimal availability and so on. And after doing all this, we need to formulate the model. And in this, we have to work very closely with the engineers, both hardware and software engineers, in order to develop a model that as well as possible reflects the architecture of the system. And then validation and verification of the model. This is another big topic in itself that needs to be worked extensively. And parameterization of the model. Again, very difficult topic, but need to be very carefully dealt with. And then solve the model. And hopefully you use a well-known tool rather than, I often see people unnecessarily spend a lot of time redoing what has been already done and write their own code. I would suggest use well-known tools. And I would also suggest hope and suggest to consolidation of all tools so that everybody benefits. And these tools can help you detect bottlenecks, do sensitivity analysis, suggest parameters to be monitored more accurately, and so on. And these tools can allow architectural what-if analysis, and of course, validate the model. To conclude then, system reliability and availability models, techniques and software packages are available for the construction and solution of reliability and availability models of real systems. And the typical method is system decomposition followed by hierarchical model composition, and sometimes fixed point iteration may be necessary. Modeling can be used to compare alternative designs and architectures. We have done that, for example, at Cisco by comparing Cisco router with the Juniper router to find bottlenecks, to answer what-if questions, for design optimization, conduct trade-off studies. We have shown that for IBM Research Cloud, and papers are written on that. At certification time, we have shown that for Boeing, and again, a paper is available on that. At the design verification testing time, we did it for IBM SIP. And configuration selection time, at one point, there was a project at Digital Equipment Corporation way back to select the configuration for a customer based on the availability requirements of the customer using these models. And at operational phase for system tuning and online control. I haven't seen as much of this as is possible for availability and reliability, but I want to see that much more so in future for computer and networking systems to use online control, these models to be used in the online control fashion. The model types that we use, non-state space models, reliability block diagrams, fault trees, and reliability graphs. State space models, Markov models and stochastic Petri nets. Semi-Markov models, Markov regenerative models, and non-homogeneous Markov models. Hierarchical composition, where top level is usually an RBD or a fault tree, and the bottom level are usually Markov chains. And occasionally, and maybe more and more so, even fixed point iteration. And solution types can be analytic closed form, if you are very lucky. More commonly though, analytic numeric using a software package, and perhaps simulation only when necessary. And software package, Sharp or similar tools are used to construct and solve such models. And structural as well as parametric assumptions means that these numbers produced should be taken with a grain of salt. Challenges, model largeness in spite of hierarchy, fixed point iteration, approximation. For example, smart grid poses a lot of challenge. And I started to work on that a little bit, but I ran out of graduate students. So if there is somebody very smart working on smart grid and wants my help, I'm happy to provide my help, but you have to be able to understand all this. Entire green book should be up your sleeve before you approach me to help. Dealing with non-exponential distributions, the algorithms need to be improved and methods of data collection need to be improved so that we have data available for the non-exponential distributions. And then more service-oriented measures rather than user-oriented measures, such as interval reliability, DPM, and so on. Combining performance, power, and failure and repair. We have done that in the case of IBM Research Cloud, but a lot more work is necessary along these lines. Model parameterization continues to evade us, particularly with respect to software mean time to failure or software failure rates. Model validation and verification, a lot more work is necessary on that. And we have written some in the Green Book, but a lot more work is necessary. And parametric uncertainty propagation, currently a lot of work is going on. I've done some work with the people in Japan and Hiroshima University. I've done some work with some Italians, such as Marco Gribado, and Vittorio Bortolessa, and so on. Model parameterization, I'm going to skip this. We have talked about this. So message to young researchers: if you can pick a real problem rather than one from literature whenever possible, there should be plenty of real problems in industry. But when you take a real problem, you have to keep an open mind. Don't go with an idea that I'm always going to use stochastic reward nets and nothing else. You may require a fault tree solution. You may require a Markov chain within a fault tree, so on. And ask questions, very pointed questions, to understand the system behavior, and listen carefully to what the answers are provided to you. And you may find a lot of answers are irrelevant. You have to find the relevant answers to your questions for the modeling. And a lot of people feel that practical problem solution is different from basic research. I found in my experience that it is possible to write scholarly articles based on work done on real problems. I have demonstrated that many times over. And whenever possible, use well-known software packages rather than writing your own code to generate and solve models. And all this stuff is available in the Green Book. And Green Book has Part 1, Introduction, chapters 1 to 3. Part 2, chapters 4 through 8, covers the entire gamut of non-state space models. Part 3, state space models with exponential distributions. And part 4 is state space models with non-exponential distributions. Consists of 3 chapters there. And part 5 is multi-level models, chapter 16 and 17. One consists of hierarchical models, and the other consists of fixed point iterative models. And then there is an additional case studies chapter. Case studies occur all over the book, but in addition, some case studies are collected in the last chapter. You can also see the flow of the book in this way, a different way. But I think the book has been written with a lot of care and a lot of experience. And I would like people to access the book. Even if you don't buy it, let your library buy it or somehow get a copy. I don't care if you get it free, but if you want to learn about reliability and availability modeling, this is an excellent source, giving you experience from 2 researchers for more than 40 years. So 80, 85 years of experience, 90 years of experience, and condensed in that book. With that, and several other papers from which I have collected the information that I have given you today. So I'm now leaving the rest of the time for questions and answers. And so at this point, I will stop sharing, if you will.
Okay, thank you, Kishore. And actually, I would invite really students to open their mic and to raise your question directly, because I think.
So yeah, you can ask the question directly, not through the chat, and turn on your video if you like.
Yes.
I'm sorry it was very fast, but I wanted to give you the gist of the overall thing. And as I said, I'm planning to do this summer a course with and somewhere in Europe, in Italy possibly, for 2 weeks. So the entire book will be presented to you in great detail.
Yes, I mean, I saw many emails are circulated on the thread that you started, Kishore. I think it's doable because there is an interest from many universities, and probably, I mean, the course might happen in one place, and I don't know, given we are getting used to this remote teaching stuff, right? So probably you can, of course, meet students, but you can probably stream the lectures through, and this will enlarge the audience for sure. So,
but I'm hoping that at least it will be for some people on in person.
Live, yeah,
There's no
sure.
substitute for in-person teaching.
Yes, sure. Actually, that's what's going on recently in Europe. So we have started. We do the two both. I mean, we teach our class, but we also stream, and there are some people. A fraction of people, of students, is remote, but the most now are attending in person again. So
And the reason I propose this is that I'm getting old, right? I still have energy, but I recently taught short courses like that at an Air Force base, and I found that practicing engineers also need this very much. And so I thought maybe I should offer to larger crowd. And so
Yes.
a lot of response already from email from Italy.
Yes.
So
I think
it will more than likely happen. I'm going to have a Zoom session with Stefano Rosso this week to discuss further how to organize this, what is the best way to organize this, because there.
I'm sorry, Kishore, I must leave the I say goodbye to everybody and.
Okay, ciao Andrea,
Ciao.
thanks for attending.
Andrea, thank you very much for showing up and answering that question.
Thank
Okay.
you.
Goodbye.
Bye-bye. Thank you.
Bye.
And so really, please raise your questions. Don't be shy. I mean, as usual, students in engineering are shy. Oh, one pop-up. Mateus.
Can you hear me?
Yes.
First of all,
Okay.
thank you, Professor Trivedi, for the nice talk. Actually, I have two questions. The first question is very simple. Is it possible to solve SMP in Sharp or SPNP package?
Yes. So there is so SPNP as an MRGP larger than SMP, and that is solved using simulation rather than we didn't implement any of the numeric solution algorithms in SPNP. In Sharp, you can do SMP. You can also do MRGP in Sharp, but MRGP only steady state solution is implemented. In Sharp, and in SMP, transient solution is implemented for acyclic SMP, and steady state solution for non-acyclic SMP. So limited form. MRGP in general will be by simulation in SPNP. So there are some available, but not fully. Yeah.
It's nice. It's nice to hear that, because some other tools does not have support to SMP solving. So, Professor, I have another question, maybe a more open question, because here in my PhD research, we are trying to use stochastic nets in the security problems. So we are facing some problems into the validation of the model, because usually security is subjective, is not really objective, because the probability of attack success may vary upon the user needs. So do you have any piece of advice on how to validate security models using stochastic nets or Markov chains or similar models? Thank you very much.
Yeah, one out I have seen is this notion of survivability. So survivability notion talks about what happens after something bad happens. So that takes out the notion, the issue of how frequently the security violation will take place. So concentrate on survivability models to make them more believable, more validatable, right?
Okay.
So notion of survivability is not as explored as it should be, but that's a very strong point in that notion of survivability as we have developed. The word is used by many people, but if you look at my papers on survivability, specifically we are talking about after the bad thing happens, right? So it takes away, in some sense, the things that is not believable, whether it's natural disaster or security or whatever. People don't want to believe that there is a time to security failure or whatever. So if
Nice.
you take it away, how does the system behave after something bad happens?
Okay. So we try to reduce the uncertainties. We assume that the attack already occurred and the system is already under pressure, and we look to the result after that.
Yeah, exactly. And then it is much more parameterizable, much more validatable, etc. Right? Much more believable. So I don't think people have been using it that way, but I would. That's my vision of how to use survivability models.
Okay. Thank you very much for one time.
Are you in Brazil or are you in?
Now I'm currently in Brazil, but I'm working with Professor Marco Vieira at the University of Coimbra, Portugal.
All right. Anybody else? I'm sorry, I overloaded. Herman, you want to say anything? Say hello. Herman, are you there? It's gone probably. It shows up here, huh? My old friend.
Okay, another student turn on his camera, but
Somebody else had a question? Don't feel bashful.
yes, don't feel shy. So
yeah, I have a question, actually a two-part question rather. So I'm from the University of Passau. I'm actually working with Professor Demer, and I've been also exploring this modeling domain for quite a while now. And
I'm not able to hear you well. Can you try and?
Let me check my microphone.
Okay, try it again slowly.
Am I audible now?
It somehow got, but go on, try. No, you're now gone altogether.
Here.
Okay, try again.
So I'm actually a PhD candidate with Professor Demer, and we're looking into the modeling of power system and ICT system interconnections, specifically with a focus on resilience. And we actually have used stochastic activity nets for the modeling of this interconnection. And I actually came across this one of your previous works, which used this interacting models. So I think it was Stochastic Reward Net on the higher level and Markov models on the lower level. And this was actually the approach we also followed, but we used stochastic activity nets on both the levels. And but where we fell short, or at least how we want to extend it right now, is one, how to accurately show the topology of a power grid. That's one thing. And the second thing is what has been actually mentioned several times is validation. What kind of validation can we use for resilience of these interconnections between the power and ICT systems? I was wondering if you have any thoughts on that.
Validation is a topic in itself. So we have divided the validation into three parts: phase validation, input-output validation, and structural validation.
Mm-hmm.
So phase validation is that you show your models to the people who know the system well,
yeah,
and explain the model, because more than likely they don't understand any of this, So first explain that, and after some time they'll say, no, this is not how the system works. And then you change the model and you keep doing that until everybody's happy. That's called phase validation. Input-output validation doesn't apply to these kinds of things, but basically it applies more to the performance modeling, that you measure the system for its for your model input parameters as well as the model outputs, and compare the model produces versus the real life. That's input-output validation. The third is structural. So find out all the assumptions you made model, see if each assumption can be either verified by system behavior or data or whatever. So you find that again in the green book. You find these things being separated out, these three. And there's also model verification versus model validation. Again, you find that in the green book.
And I was also wondering regarding inputs that you give into these state-based methods. So, for example, the rates of particular activities or transitions in stochastic P-nets. Do they follow? Since we may be focusing on systems that have not been built yet, so we may not have this data. So, what kind of assumptions can we make so as to reflect these rates of these transitions as realistic as possible?
The assumption about distributions or values of the parameters?
For both of them, actually. So I'm actually wondering that. So what for the distribution as well as the values?
Well, see, most of the time I'm dealing with real life systems, right? So there is some data available. Without the data, I don't know. I mean, you got to go buy some other papers or something like that.
Okay.
But there is always sensitivity analysis and propagation of uncertainty and all that stuff that, again, our tools, I don't know whether the tool you're using does that, but our tools do sensitivity and automated sensitivity analysis and all this stuff.
Okay. Yeah, thank you very much. Thank you for the nice talk as well.
Anybody else? So your timing worked out good, huh?
Yes, I mean, we have still 5 minutes. I think there is a room for one more question. So really, open your mic and camera.
Anybody has an answer, if not a question.
If I may ask one more question.
Sure.
Yeah, so as I mentioned, I'm looking into the resilience of power and ICT systems, specifically their interconnection. One important thing when it comes to the power system modeling is we want to capture the topology. We want to capture which buses are connected to which other buses. And so I was wondering if there is at least an idea on how to reflect topologies of power grids in any of the modeling methods that you mentioned today.
Reliability graph is a very clear topology there, right? Follow the reliability graph part of what I.
Yeah.
If you're stuck with sand, you don't get all that stuff.
That's the point. Yeah, that's the point. So
Sharp gives you all that, right? Sharp gives you all that.
Right. So we probably have to come up with a combination then. So as you mentioned, in the hierarchical modeling, we might have the reliability graph at the top level.
Sharp also has stochastic reward net, so it's the same thing as sand, right? So yeah. Sharp gives you everything. It doesn't restrict yourself to just one thing.
Okay. Thank you very much.
All right, so it's lunchtime here, and
yes, and yeah, it's almost the end of the day in Europe. So, Kishore, really, thanks for providing this interesting tutorial also this year, and really, I'm looking forward to meeting you in Italy, if possible, with really setting up this course, this more extended course, and really, thanks everyone also for attending and. Actually, if you can send me, I will send an email later on, but if you can send me the slides, I will post on the conference website, and also, I mean, I will post also the recording. So anyway, that this tutorial will be available to more people. So really, thanks a lot again, Kishore. Yeah.
Namaste.
Hope to see you. Okay. Bye-bye. Thank you. Bye-bye. Bye.
Ciao.